I'm Rakesh, and I will be talking about the front-end bottleneck in servers and what are some of the ways to get around them. This work was done at University of Edinburgh with Boris Groth and Vijay Nagarajan while I was a postdoc there. So let's see what exactly the bottleneck is. So due to the complex functionality of server applications, they are generally organized as deep software stack. And even though the stacking does a really good job in managing the complexity, it results in massive code footprints. And the working set sizes of these applications generally reach in multiple megabytes. And actually, these sizes are increasing 20%, well, at a rapid rate. And at Google, at least, search workload is growing at 25% every year. So at microarchitecture level, these working sets do not fit in the latency critical components, mainly the level 1 instruction cache, L1-I, and the branch target buffer, the BTB. As a result, there are frequent misses in these structures. And this is how these misses affect the performance. For the L1-I, whenever core goes to get an instruction from it and it doesn't find there, it needs to be brought back from the last level cache, which takes around 30 to 40 cycles. And the front end has not issued a single instruction to the backend for execution during this time, which directly limits performance. On the BTB side, whenever core goes to the BTB to check if an instruction is a branch instruction or not, and BTB does not have this information, core just assumes that it was not a branch instruction, continues to fetch instructions in the program order sequentially, and execute them. Now, after a while, the wrong path is detected in the backend of the core, and the pipeline has to be flushed. Now, this kind of pipeline flushing, again, leads to performance degradation. So if the working set size is not big enough, if the components are not big enough to capture the working set size, what are our options to eliminate this bottleneck? The first thing we can do is increase the size of these components. But that's not really a good idea because these components are latency critical and might need to be accessed every cycle. So increasing their size doesn't seem to be a good idea. So an alternative is to employ prefetching, which does not increase the size or the latency of these components. The only thing it does is it tries to bring the instruction and entries that will be used in the near future into these components before they are actually needed. So we are going to explore what prefetching options we have for these workloads. So state-of-the-art prefetching techniques can be broadly divided into two categories. First is temporal streams. The good news is they provide really high performance, but they require a lot of storage overhead. The second category is BTB-directed prefetching that does not have any storage overhead, but they provide only limited performance. And then I will present a technique called shotgun, which provides high performance, but without any metadata storage overhead or low storage overhead. OK, so let's have a look at temporal stream prefetching. These techniques operate on the principle of record and replay. So they record the sequence in which instruction cache blocks are accessed and use this information to prefetch the cache blocks next time the execution reaches that path. Let's take an example. So here we see a piece of code that has two functions spread over a few cache blocks, A to D and XY. And the dark stripes inside a block represent branch instructions. So when core executes this path, the prefetcher monitors the sequence in which cache blocks are accessed to execute this application. Now, prefetcher use this sequence of cache blocks and store it in somewhere in the history storage. Now, once we have this sequence stored in the history, we can use it for prefetching. Next time the execution reaches this path, the prefetcher knows that most of the blocks are likely to be accessed in a particular order, and it uses this information to prefetch for both L1-I and the BTB. Now, this technique provides high performance, but the problem is this storage overhead of storing this sequence of cache block accesses, which can easily reach hundreds of kilobytes. To avoid this overhead, BTB-directed prefetching takes a different approach. Instead of recording the sequence, it tries to construct it on the fly. And the way it does it is to just using branch predictor and the BTB. So let's say the prefetcher accesses the BTB with a PC, and it sees a hit in the BTB. So it knows if the branch is taken, that branch predictor will tell, where the execution will go, which next cache block will be accessed. So let's say in this case, the BTB tells the next cache block would be A. So prefetcher knows, okay, we might need to prefetch A. It goes to L1-I to check if it is already there, and if it is not there, it gets it from the LLC. Now, while this cache block is being prefetched, prefetcher goes ahead and checks and indexes the BTB with the target of the last branch it found in the BTB. So this way, it tries to find out what next cache block might be needed once A has been used. Let's say in this case, the branch is taken and the next block will be C. So it just goes and tries to see if C is in the cache or not. If it is there, nothing has to be done. In this way, the prefetcher just keeps accessing the BTB with the target of the previous branch instruction and find out where the control flow will lead to. And if the blocks on this control flow are not in the cache, it just prefetch from the LLC. So just by using BTB and branch predictor, these kind of prefetchers are able to generate the sequence of cache blocks that are likely to be accessed in the future. But what is the downside here? We have only seen the scenarios where there were always hits in the BTB. So what happens if control flow reaches a part of code that BTB has no information about? Well, in that case, there will be a miss in the BTB, and now prefetcher has no idea which next cache block will be accessed. Or this loop is broken and prefetching has to stall. To handle this situation, Boomerang, which is one of the state-of-the-art BTB-directed prefetchers, goes ahead and tries to get the cache block that contains this branch instruction, get the branches out of that to fill the BTB. This way, since the BTB now has the information about the missing branch, the prefetching can continue. However, during the whole duration when the prefetcher were trying to get the branch information from LLC, or maybe L1-I, the prefetching was stalled. So that means for every BTB miss, prefetching needs to be stalled. And if BTB misses are not frequent, there is no problem. But in server application, BTB misses themselves are frequent. So prefetching will be stalled a lot, which directly leads to less prefetching, less miss coverage, and lower performance. So let's see what we have seen so far. We have seen two types of prefetchers: temporal stream prefetcher, that they provide high performance, but they incur high storage overhead as well. And we have also seen BTB-directed prefetching that has no storage overhead, but their performance is limited. Our goal in this work is to take a BTB-directed prefetcher, since it has no storage overhead, and try to improve its performance. So let's first see what exactly is the problem with BTB-directed prefetching. The real problem is the BTB is just not able to capture the working set size of the server workloads. As a result, there are BTB misses, and each miss leads to performance degradation. What our aim here is to somehow increase the control flow coverage captured in the BTB. And to do that, we leverage the software behavior to reorganize our BTB so that it can represent more control flow in the same storage budget. So let's first understand software behavior. We have the same function, and now we are showing different kind of branches in these conditional and unconditional branches. We can divide this control flow into two components. First is global control flow that takes execution between distinct code regions. And this kind of control flow is mainly constituted by unconditional branches, such as calls, returns, trap returns, etc. And the second component is local control flow that keeps the execution within a code region. And we define a code region as the code between two unconditional branches in the dynamic instruction stream. And this kind of control flow is generally constituted by conditional branches, such as any branch conditional. Now, by dividing this control flow into two categories, we first try to understand what are their properties. So for global control flow, we observe that the working set size is very small. If we take an example, this figure shows the contribution of static branches towards dynamic branch execution for a database workload. And there are two lines on this graph. The solid line shows covers all the branches, static and local and global branches, global control flow branches, whereas the dotted line considers only the unconditional branches that correspond to global control flow. So if we look at the top 2K static branches, which is the capacity of a practical size BTB, we see that if we consider all the branches, they cover only 75% of the dynamic branch execution. But looking at only the unconditional branches, they cover 93%, which means if we have only unconditional branches in the BTB, the hit rate will be very high. So from these results, we have this insight that a global control flow can fit in a practical size BTB, whereas the overall control flow is hard to fit there. About the local control flow, we make an insight that it has high spatial locality. Most of the conditional branches tend to be close to each other in the dynamic instruction stream. Okay. And if these branches are very close to each other, we can use this spatial locality to represent this control, the local control flow in a very compact form. So using these two insights for each type of control flow, now we show how we can map the overall control flow in a BTB. And our idea is to represent it first component, the global control flow with unconditional branches. We take all the unconditional branches in the code and put them into the BTB. And since since the number of unconditional branches are small, they will generally fit in the BTB. And then for each unconditional branch, we represent the local control flow at its target region in a compact representation and associate it with the unconditional branch that brings the execution there. So this way, we are able to capture more control flow in the BTB because the local control flow is represented in a very compact form. So let's get into some microarchitectural details, how we implement this thing in a microarchitecture and how it enables L1-I and BTB prefetching. So each BTB entry now contains information about an unconditional branch, what its tag is and where it leads to, the target, and only the encoded local control flow information at the target of this unconditional branch. And this local control flow information is represented as a bit vector, where each bit tells the location of a cache block from the entry point into the region. It doesn't tell where exactly the conditional branches are in the region, it just tells which cache blocks contain those branches. Now this information is enough for L1-I prefetching. Let's see how we do that. So since the target cache block is A should be prefetched. Next, the second bit is set, which means the second cache block starting from the entry of the region will also be needed. So A+2 is also a prefetch candidate. Similarly, the fifth block is also a prefetch candidate. Now the prefetcher just goes and checks whether that block is in the L1-I or not. If it is not, it just gets the block from LLC to L1-I. So this completes L1-I prefetching. We still need to get conditional branches because our BTB only has unconditional branches. It has just the special representation of conditional branches. But the branch predictor really needs to know where a conditional branch is to predict it. And the natural question arises here is where do we put conditional branches? Because BTB now just contains unconditional branches. We don't have space for conditional branches in that BTB. So what we do is we put a small BTB dedicated for conditional branches. And whenever we enter a new region, along with fetching instructions from LLC to L1-I, we pre-decode this block to get the branch instructions out of this block. These branch instructions are then forwarded to the CBTB, or the conditional branch BTB. Now, since we are preactively filling this BTB with branch information, its small size doesn't lead to misses because we are inserting the branches into this BTB before they will be needed by the core. Okay, so to summarize, Shotgun uses a specialized BTB organization to increase the control flow coverage in the BTB. It has a BTB dedicated for conditional branches, unconditional branches, that also contains the spatial footprint at the target region of these branches. And this BTB is responsible for, is the BTB that contains most of the control flow unconditional one, and most of the storage budget of the BTB goes to this unconditional BTB. Then we have a special BTB only for conditional branches, and since we prefill it before entering a region, it's way smaller than the unconditional branch BTB, roughly 20x. Furthermore, we have a special buffer for return instructions. Technically, these instructions belong to unconditional branches, but they require way less metadata than other branches. So we have a special buffer that provides another space optimization for these kind of instructions. Evaluation-wise, we evaluate on a typical CMP with 16 cores and L1 cache of 32 kilobytes and 2 entry BTB. Since Shotgun has 3 BTBs, we use an equivalent storage budget. We use some enterprise and scale-out workloads for evaluation, and we evaluate 3 prefetchers. First is temporal stream prefetcher, and Confluence is a representative example of that. Second, BTB-directed prefetcher, Boomerang, we choose Boomerang to represent this category, and our proposal Shotgun. So if you look at the results, on average, Shotgun outperforms both Confluence and Boomerang. On individual applications, there are some applications where Shotgun, where Boomerang performs well, where there are other applications where Confluence performs well. But on average, even on each application, Shotgun either outperforms or matches the performance of existing prefetcher, except for Oracle workload, where the working set size doesn't fit even in the new BTB organization of Shotgun. To summarize, front-end bottleneck has been a critical problem in the server architectures. However, the prior work offers a trade-off between storage capacity and performance. In this work, we leverage the insight from the software behavior to come up with a new BTB organization that increases the control flow coverage in the BTB. And our insights are that global control flow fits in a practical size BTB, and local control flow favors a compact representation due to spatial locality. Then we use these insights and this new BTB organization to present a prefetcher that prefetches both for L1-I and the BTB. And such kind of prefetching erases the performance gap, mostly erases the performance gap between metadata-rich and metadata-free prefetchers. The end result is a high-performance core front-end without any metadata storage overhead. Thank you.
Do we have questions for our speaker? Could we have a look at slide 17, do you think? Yes. These two seem like they can work independently of each other to some degree, the CBTP and the main sort of unconditional. Have you been able to separate out how much of a performance gain you're getting without the CBTB and with, or without the RIB and the CBTB and with, so we can see where exactly is the gain that you're getting primarily?
If we do not have CBTB, the branch predictor won't be predicting any conditional branches because it doesn't know where the conditional branches are. So there would be lots of pipeline flushes, and the performance won't be good. How much is that? We haven't evaluated, but we expect a lot of performance loss because all of the branches are being mispredicted if they are not taken.
So instead of prefetching, if you had to retrain the CBTB, is that something?
But that's really small. So first time you enter the region, you will see all the misses, and then you will fill them from the core backend.
Any more questions?
So the CBTB is updated using like speculative information from the execution, right? Have you considered any security impact that might have substantial channels?
Yeah, that's a well, not completely, but that's an area we haven't looked at. But yeah, so no. So to answer your question, we haven't.
So here in the bitmap of local lines, you're having a 1 for every line where there is a branch?
We have a 1 for each line that's accessed in that code region during the last, when the region was executed last time. There may or may not be a branch in that region. So that's the region, that the blocks inside the region that are expected to be accessed.
So if you happen to access a block that you haven't previously accessed, do you decode the branch targets as that comes into the cache, or do you just
okay.
miss the branch target, local branch target?
If we access a new block that was not accessed last time, we do not prefetch that. That means we do not extract the branches out of that.
Any more questions? That's it then. Thank you very much.